Okay, so last day we finished talking about lines in three-dimensional space, and we went over how we describe a line in three-dimensional space using what we call parametric equations. A line is a special case of any curve in three-dimensional space. And that's what we want to look at today. We want to say, well, we could have any curve in three-dimensional space, not necessarily just a straight line. How do we represent those with a mathematical function? And we do it the same way we did as we did with lines. In fact, as I said, lines is a special case of the general category of curves in three-dimensional space. So we could have any particular, curve in three-dimensional space, and we want to have some sort of mathematical function that defines that. So we're going to do the same thing as we did with lines, because they're just a special case. We're going to say if we have some specific point P on that line, we are going to define the coordinates of that point P as a function of a parameter T. And that's why we call it a parametric equation. It's an equation that has one basically unknown, and that is a parameter. In this case, we call it T. We could call it whatever we want, K, S. Give it any letter you want. We typically use T because it's very helpful when we're explaining this to think of a particle moving along that curve, okay? And that means we can look at the position of that particle at some time t, and then look at the position of that particle along the curve at some later time t. So we make the parameter typically t, okay? So perhaps when t is equal to 0, that point is down here, and when t is equal to 1, that point is up here. So it's moving up along that curve. And last day we said that a very helpful way of defining the position of any point in space is with what we call a position vector. And a position vector is a vector that starts at the origin and ends at the point we're trying to define the position of. So let's say we want to write the position vector for point P in three-dimensional space, whether it's on that curve or not. Okay, and we call that R is the standard nomenclature for a position vector, and because it's a vector, we put the arrow over top of it. Okay, so the position vector always starts at the origin, and it always ends at the point that it is defining the position of. Now we can extend this to a curve and say we can come up with a position vector which is a function of t, which describes this curve throughout three-dimensional space. So at some point in time, r is pointing down here. Let's say r at t naught. Okay, at particular time t naught, that's where we are on the curve, and therefore we draw the position vector like that. At some later time, r is now pointing up there at t1. So as t varies from t naught to t1, r is going to continually, it's always going to start at the origin, and the head of that vector is just going to trace the curve that it's defining the position of. Okay, so we can use a position vector not just to define the position of a point in three-dimensional space, but if we can come up with a position vector that is a function of t that defines every point along that curve, well then it also defines the position of the curve. Okay, so r in this case is a position vector that defines the curve C. Okay, and the head of that arrow, of that vector, is going to keep moving as time progresses, and the point, where it is in three-dimensional space defines that vector, that curve. Okay? So we're going to use these a lot in this course, so it's a concept that you're going to have to get used to. So it is a vector, okay? So we can break it up and say, well, it has an x component that is a function of t. It's got a y component that is a function of t. Oops, j hat. And it's got a z function, a z component that is a function of t, k hat, right? I hat, j hat, k hat are unit vectors for the x, y, and z directions. Okay, so that's our position vector. So that's what we're going to use to define any curve in space. And we've already done that for straight lines. Okay, for straight lines, all we were writing were these three functions here. Okay, but you put them into a vector like this, and you've got the vector parametric form for that straight line. And in general, any curve in three-dimensional space. Okay, in the straight line, we could, if I write it like this, there's the vector form for this, for the straight line. This is only for the straight line. So for a straight line in three-dimensional space, what two pieces of information do you need to write the parametric equations for that line? You need a point on the line, right? And you need a vector parallel to the line. Those are the two things you need. And if you have them, you can write the parametric equation for the line. Okay, so here is a position vector that points to a particular point on the line. Okay, and here is a vector parallel to the line. So if we know those two things, we can write them in this form, and we've got an equation, a position vector function that defines that straight line. And if I wrote it out like this, maybe it makes even more sense to you. Oops, that's not right. Comma, Z0 plus T V3. Okay? So X equal to this, Y equal to this, Z equal to that. That was our parametric equations for the straight line that we did in the last couple of lectures. We could write them in this form to get a position vector for the straight line. Okay, this part here is all for the straight line. But in general, this is for any curve. Okay, any questions? All right, so let's look at an example. So we're asked to find the parametric equation for the curve that is the intersection between the two planes that are given. What kind of curve do you get when you intersect two planes? We've done this before, right? What do we get? What's the curve when you intersect two planes? What's the intersection form? A line, right? A straight line. We've done this before. So you could use those plane equations to get vectors and points, and you could come up with the line equation. Okay? Might be a good practice problem to do. But we're just interested in a parametric equation that describes the intersection of those two planes, which means we want parametric equations for x, y, and z such that those equations will satisfy both of those plane equations, right? If we find x, y, and z that satisfies both those equations, we know that the point that corresponds to those x, y, z coordinates lies at the intersection, or lies on the line, right? You got to satisfy whatever x, y, z's we come up with. You got to satisfy both those plane equations in order to be at the intersection. Okay? Okay, well, sometimes coming up with the parametric equations is really easy. For instance, what if we just say, let z equal t? Okay, we need to introduce a parameter because we need parametric equations. So we're going to make t our parameter, and we're going to make life easy on ourselves, and we're just going to say, you know what? The z coordinate along that line, that intersection of those two planes, is just going to vary as t does. Why not? I could actually do the same thing and just say, let x be equal to t, or let y be equal to t. Okay? If I let z equal t, well then I'm going to rewrite those plane equations. X minus y plus 2t is equal to 4. And 2x plus y minus t is equal to 2. So I've got two equations there, and I've got two unknowns, x and y, right? T is a parameter. We don't need to solve for it. But remember, what I want is I want to figure out what is z as a function of t, what is x as a function of t, what is y as a function of t. We've already said we're going to let z equal t. Now I've got two equations, two unknowns. Just solve for x and y. Using whatever method you want, Gauss elimination or whatever you've learned, okay? Hopefully you all can do that. It's pretty easy. Two equations, two unknowns is pretty easy, right? Rearrange, substitute, and solve. Okay, when you do that, you get y is equal to minus 2 plus 5/3 t, and you get x is equal to 2 minus 1/3 t. And of course, z is t. So there's my parametric equations. Okay, I've got three equations, one each for x, y, and z as a function of t. And then I could write it in the real way like this. And y was negative 2 plus 5/3 t. And z is equal to t. Okay, there's my answer. There's a position vector. The head of that vector is going to trace a straight line, which is the intersection of those two planes, as time t progresses. Okay? If you want to see if you made any errors, you can check by just putting these values for y, x, and t back into both of these plane equations and make sure that they satisfy those two plane equations. If they didn't, then you made an algebraic error somewhere. You can always go back and check. Okay? Any questions about that one? Well, here's a question. Could I have let x be equal to t?
Yes.
Yep. Could I have let y be equal to t?
Yeah.
Could I have let x and y and z all be equal to t?
No.
No, that wouldn't work. I can only make one of them equal to t, and then the other two have to be solved such that these are satisfied, right? But I didn't have to let z equal to t. I could have made x equal to t or y equal to t, and guess what? I'll get a slightly different looking equation here, right? Obviously. But there's not one unique parametric equation that defines that straight line. There's a whole bunch of them. There's an infinite number, actually. Okay? Okay, let's do another example. Let's find the parametric equation for a circle. Okay, so there's the equation for, and we're just going to deal with two dimensions here. make our life simple. There's the equation for a circle that is centered at the origin and has a radius of a, correct? It's just the circle equation. Centered at the origin, radius of a, so it's going to look like, I'm really bad at circles. There's my circle, has a radius of a. Okay? So we have to come up with how many equations? Two. One for x, one for y, that are a function of t or some other parameter. Okay? We're only dealing in 2 dimensions here, so we need 2 equations, one for x, one for y. We want x equal to some function of, let's call it t, and y equal to some function of t. Okay, well, how are we going to do that? Well, boy, that's a really bad circle, isn't it? Sometimes, finding these parametric equations is a little bit of an art. Okay, there's no hard and fast rule. This is the algorithm. Just follow it steps 1 to 5, and you're done. Okay, you have to look at what you're trying to do here, and you have to say, well, what do I have available? So we want a position vector. Make this a vector here, centered at the origin, and the tip of that traces that curve as time progresses. So that means that vector is going to spin like this, and the head of it is going to trace out a circle. So what mathematical concept does that bring to mind? Sorry? Sine and? Sine and cosine, right? Unit circle, right? Did you learn the unit circle and how to find the sine and cos of the standard angles from the unit circle, right? Okay, well, maybe we can make use of that. Does anybody remember? I made this way too small. I'm going to redraw it here bigger and make my circle, however it comes out, it comes out. Oh, that's actually not bad. Okay. The x-coordinate for that point at that particular time is there. The y-coordinate is there. That's my position vector. Okay, so if we're going to use trig, we need an angle. It's called an angle here, and I'm going to use t for my angle because t is my parameter. So at this particular point, time t, I've got an x value here, and I've got a y value there for that point on the circle. So what's x of t equal to in terms of t? A cos, say again? A cos t. Anybody agree with them? A is the radius, that's that side. So y of t is? A sine t. Did you ever think math in second year engineering would be so easy? Right? Sometimes you just have to look at the curve and you got to think, okay, what can I use to write a function that defines that curve as my parameter changes? For a circle, it's very naturally cos and sine, right? Those trig functions are based on the circle. Okay, well that's easy, we're done, right? Okay, well we could make it a little bit more difficult. Well, let me ask you this question before I do that. Would these parametric equations also define that circle? I see one nod. I see a lot of don't knows maybe. I see some don't really care. Yes or no? Would those equations also define that circle or not? No?
Yes.
Okay, let me make it even funner. What if I wrote this? With those equations to find that circle? No, why not? Radius is too big, right? Right. Okay, so let's go back to here. Did I change the radius there? No. So it's still a circle with the same radius. Did I change the center of that circle? Did I shift the center of the circle away from the origin by putting a 2 right there? No, I did not, right? So what did I change? I just changed the parameter. So if t did stand for time, what did I change? The speed of my position vector rotating around like this, drawing out the circle, right? In this case, it's at a speed, well, when t is equal to 0, where am I going to be? The position vector is going to be right here, right? When t is equal to 0. And as t increases, this guy's going to go like this, all the way around. And when t equals what? 2 pi, it's going to be back to there. So it's going to take 2 pi seconds in this case. It's going to take 2 pi seconds for that position vector to trace out the circle once. What about here? When t is equal to 0, it's still going to be here. What does t have to be to go all the way around? Just pi. Okay, so that means the position vector is going faster. It only needs pi seconds to go around once. So yes, this also defines the same circle. Okay, I could change the speed to whatever I want. I got the same circle. It's still a valid parametric representation for my circle. Okay, what about, and you know, if you're ever in doubt, all you got to do is take, I need to move this up, all you got to do is take these equations for x and y and substitute them back in here and see if they satisfy this equation. If they do, they're a valid parametric representation of the circle. If they don't, then either you made an error or they're not, okay? Okay, let's go on. What about, let me go back. So when I was describing this, these equations, let's stick with these for now. These equations, if t is really time, well, it doesn't have to be time actually. For these equations to work, I can think of my position vector being here, or I have to think of my position vector being here when t is equal to 0. I have to think of it being up here, my position vector's up here when t is equal to pi by 2, when t is equal to pi, when t is equal to 3 pi by 2, and back to 2 pi, right? And it's got to go in this direction, otherwise these don't work, okay? But maybe for the physical application of these parametric equations, maybe I don't want, what's the first thing I consider here? Maybe I don't want my position vector to start here. Maybe I want it to start up here. Okay, that means when t is equal to 0, the position vector is pointing up here, not here. These don't work for that particular scenario, right? When t is equal to 0, I get x of t is equal to, cos of 0 is 1. I get x is equal to a, that's over here. And when t is equal to 0, sine of 0 is 0. I get y of t is 0, so that's that point right there. When t is equal to 0, if I want my position vector up here, then these don't work anymore. So I have to rewrite new ones. Question is, what would be my new ones? Let's call this point B. Point B, and we're still moving counterclockwise. We're just changing the starting point. What are my new equations going to be? Is the radius changing? Nope, still right A. Are we still going to use cos for the x coordinate and sine for the y coordinate? Yep. That's not changing either. My argument is going to change though, right? I used to have just t, can't do that anymore. What do I need the argument to be equal to for the cos and sine functions when t is equal to 0? At t equal to 0, I got to be at my starting point, which is at b. Right? My starting point is now up here. So what do I need t, or the argument of my cos and sine functions, what do I need them to be when t is equal to 0? I need pi by 2. So when t is equal to 0, now the argument is pi by 2, right? I've just advanced it by pi by 2. That's all I did, advancing the argument. I added a phase shift, if you want to call it that. Okay? Okay, maybe we don't want to write it with pi by 2s. Maybe we want to write it just without pi by 2s. What is the equivalent of a cos t plus pi by 2? Now, if you go into electrical engineering, you got to know this. Maybe even later this year, for sure next year. If you're not in electrical engineering, maybe not. But it's worth, if you don't have a method of figuring this out, let me suggest one. So what we want to do is we want to rewrite cos t plus pi by 2 with some other trig function that doesn't have the pi by 2. Okay? So that basically means cos is going to change to a sine, and sine maybe changes to a cos. So if you don't have a way of doing this, let me show you what I use. If you like it, use it. If you don't like it, don't use it. Find something else. So what I always do is I take and I draw my cos function. Okay, there's my cos function. My cos function is an even function. It means it looks the same in the positive theta direction and in the negative theta direction, right? The vertical axis is a mirror. Okay, so that's cos. And my sine is an odd function. Looks like that. Okay? So if I take a cos function like I have there for x of t, and I add pi by 2, that's the same thing. What I do is I should have drawn these lower. I grab my cos function up there with my two hands, and I ask myself which hand is on the positive theta axis. My right hand, obviously, right? I take it, and I use my right hand, and I push my right hand pi by 2. So I grab that cos function up there, and I push it pi by 2, because I've got a plus pi by 2 here. Okay? So plus means use my right hand, because that's on the positive side of the theta axis, and use it to push that cos curve by pi by 2. What do I get? If I take this cos curve and I push it pi by 2, what do I get? I get a different color. Let's use a different color. Would I not get this? Right? If I take the black cos curve and I push it pi by 2 with using my positive hand, my right hand, and what do I get then?
Negative sign.
I get the negative sign, right? So that means cos t plus pi by 2 is the same as negative sine t. So that means I can rewrite this as negative a, oops, let's go back to black. Negative a sine of t. Okay? Everybody get that? Maybe I'm boring you, but chances are in a class this size, half of you probably don't have a way of figuring out these phase shifts, okay? Okay, let's look at the other one. Sine pi by 2. Well, I do the same thing. I grab my sine function with my two hands, and it's a plus, so I'm going to use my right hand because it's on the plus theta axis, and I'm going to push it pi by 2 this way. What do I get? I push my sign, I get this. What's the result? Cos, right? That red dashed line is a cos curve. So I get a cos t. Okay? So that's just a way of simplifying the curves or the expressions. Both of these are equivalent. Same thing. Okay? If it was minus pi by 2, well then I do the same thing. I grab the curve, and minus means I use my left hand because it's on the minus axis, and I push it this way pi by 2. And I see what I get, and that's my new function. Okay, so use that if you don't have a method of your own. But like I said, especially in electrical, you're going to be dealing with phase shifts. You need some way to figure that out quick, okay? All right. What else are we going to do with this one? Okay, let's go back to another, still with the circle. Let's say we go back to point A here as our starting point, but this time we want it to go this way. We want it to trace out in a clockwise direction. What do? Okay, here were our original equations. That was for starting at point A but going counterclockwise. What do we change in this case? What's our new x of t and new y of t? This is just trig. That's all this is. But we always need more practice with trig, right? So if we were moving counterclockwise, let's say after a certain time t we were there. If we were moving clockwise after the same time t we were there. Has the x-coordinate, what is the x-coordinates of those 2 points?
The same?
It's the same, right? At some later time, maybe the point is there if we're going counterclockwise. If we're, at the same time, if we're going clockwise, it's down there. Okay? There. The x-coordinate is always the same, right? That shouldn't surprise us because it's a cos function. And cos is an odd function, pardon me, an even function, right? Doesn't matter if you go in the positive direction or the negative direction, you get the same value, okay? So that means this is still the same. Okay, this was start at A and go counterclockwise. This is going to be start at A, go clockwise. What about y of t? The sine is an odd function, so we're not lucky enough that it's just sine again. What would it be? Here's our sine curve, the black one there. If I go a certain distance t this direction, I get this value. If I go the same distance in the negative direction, I get that value. What's the relationship? One is just negative of the other, right? Right? The y-coordinate for this point is here. The y-coordinate for this point is the same magnitude, just negative. So all I got to write is negative a sine t. Okay? Okay, and then there's another example there, but I've spent a long time on this. Let's move on. Oh, let's just do this. Okay, we've been assuming that the center of the circle is at the origin. Let's say that this is the circle we're dealing with. Okay, this circle is not centered on the origin. It's centered at coordinates x naught, y naught. So what would our parametric equations be for this circle? And let's just assume a starting point of A and going counterclockwise. So let's start with these. Are those going to change? If I change the center of the circle? They have to, right? What if I do this? Sine t. Does that work? I'm just guessing now. I'm trying to get you to visualize in your mind. I said it in a lecture last week that in this course it's really, really important for you to be able to, if you don't have an imagination, find one, buy one, steal one, beg for one. Find an imagination for the next 3 months, because you've got to be able to picture some of this stuff in your mind. That's the only way it works sometimes. Okay, so you got to be able to look at a function like that and imagine, okay, as time starts at 0 and goes to 2 pi, what do I get? Will that give me a circle centered on x naught, y naught? Okay, guess. Got a 50-50 chance. Yes or no?
Yeah.
Yes. You will, right? Okay, you just got to be able to picture this stuff sometime. Let's move on. And sometimes you just got to plain guess. There's no way around it. For instance, what if we gave you this equation? Okay, that's not a circle anymore, as long as a and b are not equal to each other. That's an ellipse. And we ask you for the parametric equations for that. Well, you know, x squared plus y squared equal to 1. Man, that sure looks like kind of a circle, right? Can we still do something like this? And if I'm guessing that for x, what would I guess for y, you think? Sorry? B sine t. It's just a guess. The beautiful part is I can guess, and then I can put these back into here for x and y, and I can see if they satisfy the equation, which they do. Sometimes you just have to guess and put them back into the original equation and see if they work. Okay? Okay, what about something really simple? How about this? Y equals x squared. What is that? What kind of curve is that? What do we call it? Parabola. Excellent. Okay, I need a x of t and I need a y of t. What can I use? Remembering that there is no unique solution for the parametric equation for a curve. Well, I shouldn't say that. There is one curve, and I'm going to show you that curve in a little bit. There's one curve where there's only a unique solution. It's not this one, though. Any thoughts? Sorry? Y equals t. Why not? And then x is what? Sorry? Square root of t? Oops, why did it do that? T, not 2. Remember, you can always just put it back in and see if it works. If I put in square root of t into x, I get, well, it's t. Yeah, that works, right? Or what else could you do? Usually you're going to use the simplest thing. I mean, you could come up with a really complicated expression for x and y that would satisfy y is equal to x squared, but why would you do that, right? You're wasting your time. Or you could just say, well, I could make x equal to t, in which case y is equal to t squared, if you don't like square root signs, which we typically don't. Okay? Okay, very simple. Now, those are kind of trivial examples. Here's one that's a little more interesting. It might actually have some in fact, it does have engineering applications. The circular helix. What in the world is a circular helix? Well, let me show you a picture if I can remember what to push to get the picture. Nope. Nope. This. There's a helix. Yep, exactly. Right? So if you look at a particle on this helix, traveling along the helix, what's it going to do? If it starts, say, at the bottom, right down here, right, it's going to do this. It's going to go in circles in this two-dimensional plane, and it's going to go up in this direction. A thread on a screw, for instance, okay? Well, we need a parametric equation for that. The answer's up here, so I'm going to strike it out, so if you haven't seen it, you won't be able to see it now. Okay, well, break it down. We've got 3 dimensions, x, y, and z now. The x, y dimensions, let's make this if that's z, then this is x, and this is y, or the other way around, maybe. Doesn't matter. Let's make this z. So in the xy plane, what's going on with this curve? If you neglect the z direction, what's going on in the xy plane? Circle. It's just a circle, right? So maybe we can use, x of t is equal to a cos t again, and y of t is equal to a sine t. Maybe we can use those again, in which case the radius of that helix in the xy plane has to be a, right? Okay, we can maybe do that again. What about z? Yep, z's going to do this, but what kind of mathematical function defines this? Remember, don't worry about xy right now, just think about z. What's happening in the z direction as time progresses? It's going like this, right? Very simple function. Just t, right? But maybe it has to be scaled. Okay? So that could be our parametric representation. In fact, I did it the opposite, so maybe this is actually y and maybe this is actually x. Because in the notes they have these reversed. Okay, that all depends then which direction you're going, right? Like we did in the previous example with the circle. Okay, but your position vector, or your vector which defines this, so that parameter A is going to dictate what? It's going to dictate the diameter of the helix, or the radius, and B is going to dictate how tightly packed these coils are, Because we could write the same thing, but maybe have this. Oh, yeah. Sorry? Well, I switched them up here because maybe we're going clockwise instead of counterclockwise. It's just the direction the helix is going. That's all. But what's the difference between these two position vectors? What would the helix look like? Let's assume that this is the equation for that helix. What would the helix for this one look like? What's changed in the equation? Again, I'm trying to get you to visualize.
Twice as many coils.
Twice as many coils in the same vertical distance, right? Why twice as many coils? Well, because I've doubled the speed that this vector is spinning to trace out the helix, right? But I have not changed the z. So it's still going up at the same rate, but in the second position vector, it's spinning twice as fast, which means you can have twice as many coils in the second helix as in the first one in the same vertical distance. Okay? So now you know how you can describe a spring, for instance, mathematically, right? And how you can dictate the what we call the pitch between the coils. Okay, anything else we need to talk about? One more, yes, and we'll end with this one. Okay, later on when we get to something called line integrals, this is going to be very useful to you. So let's look at this particular curve in space and come up with a parametric equation for it. Okay, so here we got our xy coordinate system, xyz coordinate system, and let's say the curve we want to describe consists of two straight line segments. So a segment C1 that looks like this, it's just in the xy plane, and then a segment C2 that looks like this, that only varies in the z direction, okay? And this point here is 1, 1, 0. So we want a parametric equation that defines that curve. Well, first of all, can you come up with one parametric equation that would describe both C1 and C2? What do you think? That would be very difficult, right? Because they're very different. We call this a discontinuity. That corner, discontinuity. And because of that, it's going to be really tough to come up with one equation. So we make it easier on ourselves and we break it up. And we say, okay, we're going to come up with a parametric equation that describes C1, and we're going to come up with another parametric equation that describes C2. Okay, so C1, we want to come up with an x of t. We'll use t as our parameter again, but again, it could be any letter you want. So what is C1? C1 is part of the line in the plane xy, and what is the equation of that in the plane? If I ask you, what's the equation of that line C1 in the xy plane? Forget about parametric equation, just the regular equation. What is it? This is the easy stuff. Quick. Y equals x, right? Starts at the origin and it goes to the point 1, 1. Y is equal to x is the equation for that plane. Line, C1, right? Okay, so what are parametric equations I could use for C1?
X equals y to the million and
Sorry?
x equals t, y equals t. Sorry, y x and t, y.
Is he right? Yep. And now to be completely clear, because we're going to be very particular here, especially when we get to line integrals, we're going to put a condition on t. We're going to say t is going to go from 0 to what? 1. Right? And what do we write for z of t? 0, because everywhere along C1, z is equal to 0. Okay, what about C2? C2 is a straight line that goes from the point 1, 1, 0. I didn't give you the end point, sorry. End point is 1, 1, 1. We're out of time, we've got to finish. Let's do it quick. X of t, y of t, z of t. Everywhere along that line, what is x equal to?
1.
Everywhere along that line, y is equal to? 1. Okay. What could we make z a function of t of? Well, now we can get a little bit fancy and we can say, well, what range are we going to give t? Well, since in the first case here, t went from 0 to 1, let's say in this case, t goes from 1 to 2. Okay, so we're going to imagine a particle starts at the origin. At time t equal to 0, it travels on C1, and then it travels up C2. So what do I write for z of t? Well, when time is equal to 0, or pardon me, when time is equal to 1, that's when we're right here. What's the z value? 0. So what if I did this? 1 minus t. Nope, can't do that. That's not right. t minus 1, other way around, right? When t is equal to 1, z is equal to 0. Yep, that's what we need. And now when z is equal to 2, or pardon me, when t is equal to 2, z is equal to 1. Yep, that's what we need too. Okay? See you Wednesday.